In this lesson, we are going to learn about gravimetric analysis. What it is a common way to use our knowledge about the precipitation reaction. That means we learn about how solubility rules are being applied to form precipitate that we can collect, okay? So using our knowledge about precipitation reaction to identify the identity of an unknown sample. A quick description of this process is basically you take a soluble sample of an unknown which is given to us, okay? And we mix with an excess amount of a known solution that is also soluble. So you have a bunch of ions in this two solution and you combine the two solutions together, which will result a precipitate. Okay, so one of the ions from this solution and another ion from the other solution will form together and become a solid precipitate that we will collect because it will fully precipitate out. That means 100% of a specific ions from that unknown solution will become solid by combining with an excess amount of ions from a known solution. So keep that in mind. So for the math part, it's really complicated, but let's go through an example and see how far we can go with this. So here is an example. Identify an alkali hydroxide. An alkali is basically in group 1A, so all those elements in group 1A. So this compound including a hydroxide. Notice hydroxide is an ion that now we know OH-, but we don't know what alkali is gonna be, because there are many possible alkali elements in group 1A. So the unknown sample has a mass of 5.30 grams, and then 4.80 grams of precipitate is collected after mixing with this solution. We have to assume that this solution right here, it has an excess amount of this. Okay, that means it has a lot of it. We don't really care because our goal is to collect the precipitate that's being formed. And of course, in this precipitate, it's gonna include the OH- in it, combining with some other ions that produce a solid. Now we mentioned before that it is an alkali group. So going back to our periodic table, alkali are elements in group 1A. We could have lithium hydroxide. Notice how the hydroxide is given to us right there. Or you can have sodium hydroxide or potassium hydroxide. So you look at the unknowns, they all have a common ions, okay? This is the ions that we will determine throughout the whole entire process. We don't know about lithium, sodium, or potassium, but we know hydroxide. So let's see how does that work. The first step is basically, if you were designing an experiment, you would use a known solution with an ions that will combine with the known ions. In this case, the known ions of the known sample is be OH-. So what ions will bond with OH will form a precipitate. It's gonna cause all this OH- to fully precipitate out. That way we can collect it as a solid. So here is an example of a known solution that we can use to react with an alkali hydroxide to form a solid precipitate that we can collect. For instance, we can use copper nitrate. Is this the only possible chemical? No. You can use other soluble compound that can mix with this and it will still form a precipitate. But in this case, we use copper to nitrate. Remember, any compound with a nitrate will be soluble. Going back to our solubility rules. And then, of course, we look at this in terms of a net ionic equation, okay? So let's look at this. Then I use a generic symbol letter X. That X is to represent any alkali, could be lithium, sodium, or potassium in group 1A. So keep that in mind. That's the tricky part. We don't know which one it is, but we know that this one is also soluble. How do you know? Because our only rules about solubility is this. Any compound with an alkali or a nitrate or ammonium, all of them will always soluble. Therefore, this one we know is going to be soluble. Then by using these two chemicals as our reactant, we can use a precipitation reaction or a double displacement process where the copper and the positive metal alkali is being exchanged. It's called double displacement. They exchange each other's place, okay, and produce our product. In this case, copper is gonna form with hydroxide, and copper hydroxide is a solid precipitate because it is not one of the rules of solubility that we have to remember. When copper and hydroxide bond together, they form a precipitate. Because the only rule that we really have to remember about solubility is when a compound has an ions of an alkali or a nitrate or ammonium. In this case, this doesn't have any of those conditions, so therefore it has to be insoluble. That means it will stay as precipitate. And here is our nitrate. Of course, this one is going to be soluble. That's why we have as an aqueous. So be careful with that, okay? As I perform my double displacement, I have to balance out. Here I have 2 hydroxide because of copper 2 right here, okay? Copper 2 plus. So if I have 2 hydroxide over here, I have to put a 2 right there. That's why I balance it for you, okay? And then if I have 2 of hydroxide and 2 hydroxides balanced, but then we look at the nitrate. We have 2 nitrate there, but over here we only have 1 nitrate, so we put a 2 there. So the coefficient would be 2 and 2. And that's how you balance out a chemical reaction. So it's important to balance the chemical reaction before we continue on. The next thing on the list is that I'm going to write a net ionic equation so to show that how a precipitate is being formed. First of all, this one is soluble, okay, because of the nitrate. So we break into ions. We have Cu2 plus and 2 nitrate ions. How do I know it's 2 plus? That is because each nitrate is NO3 minus. So we have 2 of that. That copper must be 2 plus. And then we have the next compound, an alkali hydroxide, which is represented by X. We know that it's going to be 2 because remember, we balance out before we write our ions equation or ionic equation. So 2X plus, and then hydroxide is forming ions in this solution as well. Since both reactants are soluble, they exist as ions, so these ions will combine together in different combinations to form a precipitate, if it's possible. And we have copper combined with hydroxide. This is not soluble, and it forms a solid, and it remains a solid forever. Where the rest of the ions were the alkali metals, and the nitrate will remain as an ions or an aqueous ion in the solution. So keep that in mind, that this is now a solid that we can observe and we can collect. Now our net ionic equation would be, of course, we're going to cancel out our spectator ions, which are the ions that exist on both sides of the chemical equation. In this case, NO3, NO3, the alkali metal, and X, and that give us what? Cu and hydroxide, and give us our product that's being formed as a precipitate. Here you have the copper in aqueous form as an ion, and here we have hydroxide that will form the copper hydroxide. So these 2 ions combine together to form this solid precipitate. Now, one thing we want to remember that this solid is now something that we can collect, we can filtrate. And if we can filtrate, we can actually dry it up and we can weigh it. So that's how the process works. Once we observe this solid, we're going to use a filter system. We're going to filtrate it out. So that way we will collect 100% purity of copper hydroxide. And then from there we can do more math involved with it. So using our knowledge about this precipitation process, we can solve for the mass of copper hydroxide that's being formed. If we were to look at the problem usually given to us on a test, the mass of the precipitate has to be given to you. So make sure you read the question carefully. In this case, if we go back, it is given to us as 4.80 grams of precipitate. And remember, it doesn't tell you that precipitate for a reason, because they want you to do all this math right here, okay, to determine what is the precipitate gonna form. Now, we filter it out, we collect precipitate, we're gonna dry it, and we're gonna weigh it, and we get the mass. That's how the whole entire process is gonna work every single time for any gravimetric analysis. And once we get the mass of the precipitate, what can we do? We can convert to mole or precipitate. Why do we want to convert to mole? Because mole is a universal unit that converts from one chemical to another chemical. It's called molar ratio on our stoichiometry flowchart, going back to the idea that anything can be converted from one mole A to another mole B if they have some kind of relationship, either a chemical formula or a chemical reaction. In this case, it is a chemical formula. And notice how we focus hydroxide is within this chemical formula. So let's look at an example. In this case, if we look at copper hydroxide, we can determine a mole to mole A to mole B relationship. That is, 1 mole of the whole entire compound or the whole entire formula is equal to moles of that specific part. We are looking for hydroxide specifically because hydroxide is in the unknown sample that's given to us. So therefore, has how many moles of hydroxide? Using our knowledge about reading chemical formula, that 2 indicate there are 2 of hydroxide. So that's why we have 2 moles of hydroxide. Since we know the mass of the precipitate as copper hydroxide, we can actually convert to mole by using the molar mass. And if you don't remember how to find the molar mass, it's basically the mass on the periodic table for copper, oxygen, and hydrogen. And you add them together and it turned out to be 97.55 grams of copper 2 hydroxide. So the copper 2 hydroxide is going to cancel out in gram. That would give us mole. And now we have mole of copper 2 hydroxide. Isn't that beautiful? Because with mole, we can now convert it and find what? The ions of hydroxide which exist in our unknown example, using our mole A to mole B ratio. Here I have my moles of copper 2 hydroxide, and we get our mole ratio from the chemical formula itself, 1 moles of copper hydroxide relative to 2 moles of hydroxide. This one cancel out and give us moles of hydroxide. This is the amount of mole of hydroxide that exists in the given sample of how much is it again? In our sample of 5.3 grams. So this is how many mole that exists in 5.30 grams of the unknown sample. Isn't that beautiful? Now we know how many mole there are in that sample. We can use this mole and convert it to mass, because there is something beautiful about mass that we talk about later, and it's called mass percentage or mass percent composition. But for now, let's talk about how we can convert the moles of this ions, hydroxide, into mass. Again, whenever you want to convert between mole and mass, think about molar mass, or 1 moles of that substance equal to the number gram of that substance. So we have this from a periodic table, okay? O plus H, the mass of oxygen plus the mass of hydrogen, give us 17.02 grams. So the moles of hydroxide cancel out and give us the mass of 1.67 grams of hydroxide. Now this is the total mass of OH in that given sample. Remember, that given sample is 5.30 grams of unknown. Now all this is being forced to fully precipitate out because we are treating with an excess solution that has copper ions that will react with the OH minus to form CuOH2 as a solid. See how beautiful that is? So once we have the mass of the ions, what can we do? There's a beautiful concept called mass percent composition. Think of the word composition, right? That is, what is the component in the chemical formula? What is the component that exists to make a complex compound? In this case, let's look at something very simple as water, H2O. H2O is water. We're always made of 2 hydrogen and 1 oxygen. And it's always like that throughout the whole entire universe. If it changed to become something else, it's no longer water anymore. What does that mean? If we look at the periodic table, right? A periodic table has specific values of mass for hydrogen as well as oxygen. So if the number of hydrogen stays the same and the number of oxygen stays the same, their mass composition must stay the same. And using our mass percent composition, we can identify the identity of a substance. So how does that work? Mass percent composition can be equal to a very basic formula, is the mass of the part divided by the total mass of the whole. Now what are the part? If we look time 100, Now, what are the parts? The part can be a specific element in a compound, a specific ions in a compound. All those things are part of a compound. And what is a whole in this case? What is the total mass of the whole? The whole will be the total mass of the whole entire compound, and in most cases is compared to the relative molar mass, or in this case, it is a given mass in the sample, which is 5.30 grams of our unknown. So the mass of the sample is the whole sample, that including the hydroxide ions. In this case, going back to the part would be the hydroxide part in the unknown sample. See how beautiful that is? We just figured out that, hey, I have 1.67 grams of OH in the sample, right? We solved it over here. 1.67 grams of OH in the 5.3 sample. So the part is going 1.67 grams of OH, and the whole is the whole entire sample, 5.30 grams of sample. And we time by 100, give us 31% composition of hydroxide. So there are 31.5% of hydroxide by mass in this compound. Now, going back to the fact that's right here, molar mass is also can be used to represent percentage. What does that mean? Let's look at some example. Here I have lithium hydroxide, right? I can use a periodic table to find the percent composition of hydroxide relative to the whole entire compound. So again, the molar mass of hydroxide using a periodic table is 17.02 grams, and then the whole entire compound right there is a molar mass of lithium hydroxide, giving us 23.96, and we find the percent composition of 71.04% of OH minus, or hydroxide. So this is the percent of hydroxide in lithium hydroxide. So again, the idea is to find the mass percentage of composition relative to hydroxide, because in our sample we have 31.5% of hydroxide. Now we are going to compare it to the list of possible alkali hydroxide using our periodic table. Another alkali hydroxide is NaOH, where we have 17.02 grams, again relative to hydroxide, and this is the molar mass of NaOH, give us 42.5% of NaOH minus. That's how much hydroxide is in NaOH sample. And then we have KOH, or potassium hydroxide. Here again, 17.02 divided by 56.112 grams. This is again the molar mass of potassium hydroxide, and it turned out to be 30.3% of hydroxide. So notice how each one of them has different percent composition of hydroxide. And based on our knowledge of different percent by mass, we can compare them together with our unknown sample. Look at that, isn't that beautiful? We have 31.5% by mass, and we have 30.30. They are almost the same. So therefore, your unknown must be potassium hydroxide, because of the percent composition is the same. So that's how you apply the concept of mass percent composition to identify the identity of our unknown. I understand this is a very complicated process, so I'm going to draw a quick flowchart for you. First of all, we have our mass of unknown, right? And from our unknown, we have a specific ions that we're looking for. And this ions that we know, in this case OH minus, will combine with another ions to form a precipitate. That we can collect and dry it and weigh it. So we're going to get the mass of precipitate. Okay, and once we get the mass of precipitate, we can solve for the mole slash mass of ions. Okay, once we find the mass of the ions in the sample, in the unknown sample, we can determine the mass percent of that ions in the sample. And then we're gonna compare it to the possible unknown based on their mass percent as well.